So welcome to another Maths with Paddy video where we talk about an idea or term from mathematics and do an example always in less than 5 minutes. So today, the term we are going to look at relates to the limit of a polynomial. Okay, so for any polynomial, so for any polynomial, okay, let's say the polynomial is given by p of x. Okay, and this is equal to C0 plus C1 by x plus a lot of other terms, and we go all the way up to an nth term, which is Cn by x to the power of n. Okay, so for any polynomial like this, okay, if we get the limit of it as x approaches a of p of x, limit of this polynomial. So this it'll be equal to the polynomial evaluated at a, which is c0 plus c1 by a plus a lot of other terms plus cn by a to the power of n. So this is just equal to the polynomial p evaluated at a. Okay, so that's the theorem we're going to prove today. So there are two things we need for this. So, okay, one of the kind of rules of limits is that when we take two functions, okay, such as f of x, okay, and if we add g of x, so if we're getting the limit of the addition of two functions, this is just equal to the limit of the first function, f of x, plus the limit of the second function, g of x, okay, g of x, yeah, okay. And then the second thing we'll need is the nice result that we had in another video where we talked about the limit of a product of two functions. So nice result, okay, is that the limit, okay, of an nth product of the same function. So if we have f of x, okay, and uh, that's multiplied by itself n times, okay, this will just equal to the limit of the function. So you get the limit of the function, get the limit of f of x, okay, and then you can just multiply it n times in order to get the result. Okay, so let's get on with the proof. Okay, so the proof, okay, is that if we take the limit as x approaches a, x is approaching a, of our polynomial p of x, okay, so this will be equal to the limit as x approaches a of the polynomial. So the polynomial is c0 plus c1 by x plus a lot of other terms plus cn by x dn. Okay, so this will equal, using the addition rule for limits, the limit as x approaches a of c0 plus the limit as x approaches a of c1 of x. Okay, all these c's are constants, plus a lot of other terms, plus the limit as x approaches a of cn by x dn. Okay, that's the result of the addition rule. So if we get the limit of a constant c0, that oops, just rewrite that. C. So that's c0, okay? And if we have a constant limit of c1 by x, okay, we can take that constant outside the limit function. So it's c1 times a limit as x approaches a of x plus a lot of other terms plus the limit as x. Oh yeah, I need the constant out here. Okay, so c n by the limit as x approaches a of x dn. Okay, right, okay. So then this will equal c0 plus, so the limit as x approaches a of x is just going to be a, okay, c1 by a plus a lot of other terms plus, so cn by this limit is just based on the nice results that we had earlier. So this would be Cn by a to the power of n. Okay, so this is just equal to the polynomial p evaluated at a QED. Okay, so that's our result. Okay, so this is handy whenever you see polynomials. So we'll do a uh, quick example. So the limit as x approaches a constant, in this case 5, of the simple polynomial x squared minus 4x plus 3, okay? So just sub in 5, evaluate the polynomial at x is equal to 5, okay? So it's equal to 5 squared minus 5 times 4 plus 3, and if you figure that out, it's going to be 8, okay? Thanks for your time. See you next time.